Hello, I am Dr. Zenya Worth, and in this video, we will be discussing derivatives and the basics of integration. We will discuss polynomial differentiation, the sum and difference rule, as well as the product and quotient rule for differentiation, derivatives and special functions, and the chain rule for differentiation. We will also introduce the basics of integration and chain rule and U substitution for integration. Let's start with the definition of a derivative. The derivative of a function is the rate of change of that function over an infinitesimally small length, or time, or whatever unit is changing. It is essentially a very, 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 very tiny slope at a given point. It's an infinitesimally small slope. Mathematically, it's described by this expression. The derivative is the limit as delta x approaches 0, and it's typically denoted as f prime of x, f apostrophe of x, or d over dx, assuming that x is the variable you want to differentiate. F prime of x is equal to dy over dx is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. That is called the limit definition of the derivative. There are certain rules with regards to differentiation, and as part of this review video, we'll go through them. For polynomials, the derivative of the polynomial is based on the order. There's a general expression for a polynomial of order n. The derivative is n times x to the n minus 1. So whatever power x is raised to, you move that to the front, that number to the front, and you do n minus whatever number minus 1 to get the derivative. If there is a constant in front of the polynomial, that remains there and is multiplied by the n value as it comes down to the front. If you have a constant by itself with no x, the derivative of a constant by itself is 0 and the term disappears. The derivative of a first order polynomial, which is just x, is 1 because x of 0, where 1 minus 1 is 0, x of 0 is equal to 1. So the derivative of x by itself is just 1. Here's an example for us. We have the function f of x is 6x cubed plus 5x squared plus x minus 3. To take the derivative, we take the derivative of each of these polynomial terms independently. You bring down the 3 of your first third order polynomial. So 3 times 6, the constant remains. And then 3 minus 1 is 2. So you end up with a polynomial with the order 2 or x squared. Do the same thing for 5x squared. You bring the 2 to the front, 2 times 5. And then 2 minus 1 is 1, so you have x. The derivative of x by itself is 1, so you have 1. And the derivative of a constant is 0, so that term will cancel out. So your final derivative here is 18x squared plus 10x plus 1. This rule also works for polynomials in the denominator, because these are actually negative polynomials. The polynomial will seem to increase in value because it becomes more negative, but you are doing it correctly. And as long as you remember that a polynomial on the bottom is negative, it is the same process. If f of x is 1 over x squared, that's the same thing as saying x to the negative 2. So the negative 2 would come to the front in the derivative, and then negative 2 minus 1 is negative 3. So the derivative there is negative 2x to the negative 3, or negative 2 over x to the third. The sum and difference rules for derivatives are the following. For if you're taking the derivative of two functions added together, just like we did with those polynomials, where it was x to the fourth plus x to the third plus x to the second, etc., you can take the derivative of each of those functions independently. So you just distribute the derivative, and then you add them together. Same thing for the difference. If you're taking the difference of multiple functions independently, you take the derivative of each function and subtract them. If you're multiplying or dividing functions, it becomes a little more complex. If you're multiplying functions, in order to get the derivative, you need to keep the first function f of x by itself, and then take the derivative of the second function, g of x. And then to that, you add g of x by itself times the derivative of f of x. So you get f times g prime plus g times f prime. If you're dividing two functions, it becomes slightly more complicated. You still have f prime g plus g prime f, like we did for the product rule, but now you divide that entire expression by g of x squared. So you square your initial function g of x and put that on the bottom. Here are some derivatives of special functions. Remember, for the natural logarithm ln of x, the derivative of that is 1 over x. The derivative of the logarithm of any base for x is 1 over x ln of a. So if this was a log base 10, log 10, it would be 1 over x ln of 10. For exponential functions, e of x, the derivative of e of x is actually e of x. And here are some common trigonometric functions and their corresponding derivatives. Please keep a careful eye on when a function has a negative sign, when its derivative has a negative sign versus when it does not. Let's talk about the chain rule. We use the chain rule to differentiate composite functions that have multiple functions embedded in the same function. The chain rule states that you take the derivative of the outer function and you multiply it by the derivative of the inner function for as many embedded functions as you have. This can get complicated if you have multiple layers of functions. In this case, we have f of g of x. So g of x is embedded in the function for f of x. The derivative of that would be f prime of g of x, where you keep g of x where it is, and you take the derivative of the outer function multiplied by the derivative of the inner function. If you have two functions embedded in f of x, then you have to do that multiple times. Derivative of the outermost function first, kind of like an onion, you go in. Derivative of the outermost function first, and you keep the inner functions where they are, you don't change them, plus the derivative of the second outermost function, and you keep p of x, times the derivative of p of x. So you have three things multiplied together here. Let's do an example. In this case, f of x is the square root of 5x cubed plus 2x minus 5. It's important to recognize that the square root by itself is its own function because the square root of x is a function. So just because x is getting a lot larger in here, there's a lot more going on to the square root, does not mean the square root is not its own function. So you need to take the derivative of the square root, but you also need to take the derivative of everything underneath the square root as an independent function, which is 5x cubed plus 2x minus 5. So you take the derivative of both according to that formula for the chain rule. First, I take the derivative of the outer function, so in this case, the square root. I bring the 1/2 down because the square root is just x to the power of 1/2. I bring the 1/2 down. 1/2 minus 1 is negative 1/2. So my first expression is 1/2 times g of x, my internal function, to the power of negative 1/2. But then I need to take the derivative of this function inside. And that derivative is 3 times 5, x squared, plus 2. And minus 5 goes away because it's a constant. So it's actually 15x squared plus 2. Which means if we simplify this and bring this to the bottom since it's negative, the derivative of f of x is actually 15x squared plus 2, the derivative of g of x, divided by the square root of 5x cubed plus 2x minus 5. Let's do another example with trigonometric functions. So this is a very common way we see this. F of x is the sine of 5x cubed. Well, there's the sine of x as your outer function, and then there's 5x cubed as your inner function. So you need to take the derivative of both. You need to take the derivative of the sine function as well as the derivative of the inner function, 5x cubed. The derivative of the outer function, sine x, well, that's cosine of x. But in this case, you keep g of x where it was, and it just stays there. So the derivative of sine of 5x cubed is cosine of 5x cubed times the derivative of 5x cubed. And that is cosine of 5x cubed times 15x squared. So the whole derivative of this entire function is 15x squared times cosine of 5x cubed. These problems can get complex very quickly as you add embedded functions. So be sure to be careful about writing out each function very carefully and finding the derivative of each one. Now let's kind of switch gears and talk a little bit about the basics of integration. Integration is the opposite of derivation. It is a mathematical representation of finding the area under a curve f of x. The derivative was the infinitesimal slope. The integral was the area under a curve. Mathematically, it can be described by the fundamental theorem of calculus, which is this. If a function is continuous in the range a, b, so f of x is continuous, there's no breaks or discontinuities or things, then the integral of f of x dx is equal to a of x. And the derivative of a of x is f of x. The fundamental theorem of calculus essentially defines the antiderivative as the opposite of the derivative. If f is a continuous function of x defined on the closed interval, and capital F is another function such that the derivative of capital F of x is equal to small f of x, then if you have a specific domain of a closed interval a and b, the integral from a to b of f of x is f of b minus f of a. This expression determines or describes how you use integration to actually determine the area. A and B are values, and you actually find the function of the expression at these two different values, subtract the two, and you get the actual value of the area. Because integrals are the opposites of derivatives, we can use what we know of derivatives to find the corresponding standard formulas of integrals, which are these seen here on the right. The arbitrary constant c is included because these are indefinite integrals, because they're not evaluated over a set of limits from a to b. These are just general forms of these integrals, so they're always going to have a constant. You can see the integral of e of x is also e of x. The integral of 1 over x is ln of x. The integral of secant squared of x is tangent of x. So you can see how these are very closely related to their derivative functions. Adding and subtracting of integrals is very similar to the adding and subtracting of derivatives. If you have the integral of f of x plus g of x, you can split that into the integral of f of x plus the integral of g of x. Same thing for your subtraction. Additionally, if a function is multiplied by a constant, for the derivative, we keep the constant separate, and we do the same thing for integration. We take the a or the constant outside the limits of integration. We don't worry about it. We take the integral, and then we multiply that by a. Chain rule becomes a little more complicated, just like it became more complicated for differentiation. To integrate a composite function, we apply the chain rule in reverse. We use a method called U substitution to do this. There are various steps involved. I kind of broke it down into 3. Step 1 is to assign a function u of x that describes one of the composite functions, and take the derivative of u of x, where the derivative is d over d of x of u of x. Then we substitute u of x and du in for the original function and perform an integral of u du instead of x dx. Once the integration is done, we place our original expression in for u of x. The key here is to apply a clever and correct expression for u of x, so that it does help us actually simplify our original expression into u du, and we can easily integrate it. So that's where the genius comes here in u substitution. Here's an example for us. We have the integral of x squared times square root of 4 plus x cubed d of x. We need to assign one of these functions for u of x. We recognize that the derivative of x cubed is x squared. So we should actually assign u of x to be the higher order function. So in this case, it's going to be 4 plus x cubed. If u of x is 4 plus x cubed, then du of x is the derivative of 4 plus x cubed, which is 3x squared. Well, that's very convenient because I already have an x squared in here, and I know I need to get rid of that somehow. We're going to substitute u of x and du into our original integral. Unfortunately, we have to divide the expression by 1/3 because our original integral has x squared, but our derivative is 3x squared. So we're actually going to multiply the entire expression by 1/3 to remove 3 here and make it look like the original function. So in this case, the integral of x squared times the square root of 4 plus x cubed is 1/3 the integral of square root of u, because u is 4 plus x cubed, square root of u times du. So we simplified this nicely, and we can find the integral of square root of u very quickly, and then we're almost done with the problem. So we're going to integrate 1/3 the integral of square root of u times du. Remember that the square root is 1/2. And remember that when we integrate, we actually add. So we don't subtract an integral, we add. So in this case, it would be u to the 1/2 plus 1 is u to the 3/2. And then we divide by that constant now. So u to the 3/2 divided by 3/2 is the actual integration of square root of u. We have the 1/3 in the front, so we still have to worry about that. But this is the integral, and now we simplify. So 1/3 times 2/3 is 2/9. U to the 3/2 plus c. This would be the expression for the indefinite integral of square root of u du. Finally, we substitute our original expression for u of x back into where we started. Since the integral is 2/9 u to the 3/2 plus c, the actual final expression for the integral is 2/9 times 4 plus x cubed to the 3/2 plus c. I encourage you to try these practice problems. First, differentiate the following functions, and then take the integral of the derivative. So do it one way and then try to do it backwards and see how different your answers are. You should see that they match up very well. It helps you practice your differentiation rules for polynomials, for the product rule, for the multiple functions here, so the chain rule, and for the chain rule again. And then take the interval, practice your U substitution, practice your chain rule, practice your integration of multiple functions, your product rule, and things like that. And then see how your answers compare. I hope you find this video useful for your class.